Morning everyone, I'm Chenagala Sonith Yadav and this is in Tech Talk. I am from CSE Data Science and this is an AAT Tech Talk, part of my first semester. Today's topic is design and fabrication of indigenous low-cost water filter using activated carbon prepared from low-cost minerals. The present study aims to develop and design a water filter unit for groundwater using a clay pot. We're using a clay pot and a cartridge filled with activated carbon to filter the groundwater that is found in rural areas. Efforts are being made to develop low-cost activated carbon from locally available agricultural waste such as areca nut husk. We'll get to areca nut husk later. That is used to make a low-cost activated carbon. Locally available filter materials, sand and sponges are used as filter media. So the cartridge we are using uses areca nut husk, sand and sponges to purify water. The main focus of experimental investigation is to test the activated carbon absorption capacity for different water parameters. So the focus of the experiment the main focus of the investigation is to test the activated carbon absorption capacity for different water parameters. So the introduction with increase in population and the industrialization, worldwide groundwater quality is becoming polluted. So before 1950s, there weren't so many people, and people used to use bore wells and pumps which used groundwater, and that was people's means of fresh drinking water. But now, due to industrialization and urbanization of our country, much of the waste is dumped onto ground, and which further seeps down and reaches the fresh groundwater that is available to us, and it reaches groundwater reservoirs, and through which the groundwater becomes harmful for daily, domestic and daily use. The main sources of pollution are excessive pumping of groundwater, disposal of agricultural waste, and our urban and industrial wastes. So we are exploiting groundwater too much, and which leads to depletion of groundwater, and we also dispose agricultural waste such as weeds and also fertilizers and manures which have harmful chemicals that seep into the ground and reach the groundwater reservoirs. And urban and industrial waste refer to factory waste like toxic waste from plastic factories, and other waste from urban households that are flushed in that go deep down to the drain, which infects the groundwater reservoirs. According to the World Bank, India relies heavily on pumped water from aquifers, which accounts for about a quarter of global demand for groundwater. So the World Bank tells us that India relies heavily on pumped water from aquifers, which accounts for about a quarter of global demand of groundwater. India is known for its population, and we are also using a major part of groundwater. Which we are also using a major part of groundwater. That is about a quarter of global demand for groundwater, and also about 80% of India's 1.35 billion residents depend on groundwater for both drinking and irrigation. Now, that is a very high percentage that depend on groundwater for the daily lives. This is why groundwater is very important to us in daily life, and the pollution that is being caused to the groundwater is harming everyone is harming everyone's daily lives, and this should be reduced further. Groundwater is being pumped at a faster rate than it is recharged by rain. We all know how groundwater is formed, right? There's a water cycle. this water from the sea gets evaporated, and the clouds form. And when excess clouds are formed and they cannot hold the pressure of the water anymore, it rains. And when it rains, the ground absorbs the water, and this goes into the ground, and we find groundwater reservoirs because of this phenomenon. But the groundwater is being exploited and pumped at a faster rate than it is being recharged. That is, we are exploiting the groundwater at a faster rate than we actually should. Negative effects of groundwater depletion have been observed. They are deterioration of water quality, increased pumping costs, and drying up of wells being some of them. Uh, det- uh, Deterioration of water quality. That is, we are getting lower quality water, and also getting polluted water from the waste that are being dumped onto the land. And due to we are exploiting groundwater so much that we have to dig deeper. We have to dig deeper to find groundwater, thus increasing pumping costs, and drying up of wells being some of them. And yeah, and in the 20th century, wells and pumps used to be the main source of daily water. But now, due to depletion of groundwater, pumping costs are increased as the groundwater is seeping lower and lower, and and the wells are drying up due to overexploitation of groundwater. The changes in physical and chemical parameters of groundwater depend on the geological structure of the area, anthropogenic activities, and the depth of the well. So the changes in the physical and chemical parameters of groundwater depend on the geological structure of the area. Like the geological structure of the area means plains, mountains, deserts, and all these factors. In deserts, wells are usually dug way deeper than they are in plains. So that is an example. Groundwater is contaminated with total hardness, chloride, fluoride, iron, acidity, and alkalinity. The excess quantity of chloride and alkalinity in water gives unpleasant taste, and high chloride content leads to corrosion. So, to combat the toxicness of water, we are using chemicals other chemicals to combat the toxic, such as chlorine and other alkalines. But excess of these chlorine and alkalines can also lead to excess of these chlorine and alkalines can also lead to unpleasant taste, and high chloride content leads to corrosion. It leads to corrosion, right? The high content of total hardness, calcium, and magnesium leads to encrustation in water supply structure and adverse effects on domestic use. So uh, we use soft water in our daily use. That is water which forms lather with soap, or it is less harsh on our bodies. But hard water contains calcium and hard water contains calcium and magnesium bicarbonates, and total hard water contains fluorides and chlorides, which are very harmful to chlorides, which are very harmful to our body and cannot be used in domestically. Agricultural waste materials such as coconut shell, peanut shell, and tamarind indica fruit shells, rice straw, etc., are used to make activated carbon. So, in this case study, we are going to see we're going to make activated carbon with one such agricultural waste known as areca nut husk. There were attempts to make water to purify water. That is, in 2016, Joshi and Adhikari worked on the preparation of activated carbon using areca nut husk as a precursor material for the removal of fluoride ions from aqueous solutions. Lewin et al. In 2015 worked on the preparation and characterization of activated carbon from rice husks for methyl orange absorption in aqueous solution. The present study focuses on the removal of chemical constituents such as hardness, chlorides, alkalinity, and acidity using naturally available low-cost absorbent areca nut husk. Yeah, that is, we'll get to areca nut husk in just a minute. This technique can prove an effective and cheap water purification system in rural areas. The areca nut husks are sourced from locally available agricultural waste. So we are doing this in Shivamogga, that is in Karnataka. The case study here is based in Shivamogga, Karnataka, and we find areca nut husk abundantly there, and we are using it to make activated carbon for our water filter. Right. So the methodology to make activated carbon is right here. Yeah. So A is the sample collection and transportation. Groundwater samples were collected from selected bore wells from local village area of Shivamogga, Karnataka. As I said, this case study was conducted in Shivamogga, Karnataka, where samples from some select bore wells were selected. Pre-cleaned PVC, that is polyvinyl chloride, 2-liter capacity cans, PVC cans of 2-liter capacity were rinsed with distilled water before collecting samples. So we are using distilled water to clean this because we need to maintain the hygiene and do not mix any of the other dust particles that were in the cans previously. So we're keeping it clean. Water is let out for 3 to 5 minutes to let all the impurities out before collecting the samples. So water is let out for 3 to 5 minutes to let all the impurities out before collecting the samples. So when you're collecting samples through bore wells, we use pumps and pipes to do it. So, but sometimes there is accumulated dust in these pumps and pipes. To eliminate this accumulated dust, we are letting water flow from 3 to 5 minutes to let all the dust and all the impurities out before collecting the clean samples. The containers are describing the date, storage time, and sample location are labeled. The collected samples were shipped to the laboratory within 2 hours. So all the containers were labeled with date, storage time, and sample location, and the collected samples were shifted to a laboratory within 2 hours. So this is areca nut husk, right? This is the husk, and this is areca, the fruit areca. We're using the husk to make activated carbon, right? This is the husk, and this is the fruit inside. Samples were analyzed for the various physiochemical parameters according to the standard procedures. Total 9 trials were taken to derive the results. So the process that I'm going to describe now was done a total 9 times before deriving the results. The observed results of the physiochemical analysis were compared before and after the water purification. Like when we after letting the water go through the cartridge in the clay pot, and as soon as we collected it from the bore, both of those were compared. Shivamogga district has been selected for this work as areca nut grows in abundance. Yeah, as I told you, Shivamogga district was selected for this work because there is an abundance of areca nut grown in Shivamogga. In the present study, we are going to use areca nut husk as a precursor for the preparation of activated carbon for water treatment. So we're using areca nut husk as a precursor. Precursor is like, how do I tell you? Yeah, precursor is like a base material for preparation of activated carbon husk. Right. So we use the husk of the areca, and this is the fruit. We only use the husk for preparation of activated carbon. So here's the process. Preparation of uh, areca nut husk activated carbon. The areca nut husk fiber, that is this fiber, is cut into small pieces and dried under sunlight and then placed in a hot air oven for 24 hours at 60 degrees Celsius until the remaining moisture is completely evaporated. Oh, sorry. Yeah. We're collecting the fiber, cutting the fiber into small pieces and drying it in the sunlight, and then placing it into an oven for 24 hours at 60 degrees Celsius until the remaining moisture is completely evaporated. So we do not need moisture for preparation of activated carbon. 25 grams of NaOH pellets were dissolved in 1 liter of distilled water. Then 100 grams of areca nut husk was mixed with NaOH solution in a beaker and stirred in a magnetic stirrer at 80 degrees. All of this is just the process, and I'm just going to run you through it. Beaker is extracted with a magnetic stirrer and the contents are cooled and rinsed with distilled water 4 to 5 times until the pH of the water is close to 7. Then the water precursors were then placed in the oven at 110 plus or minus 5 degrees for 24 hours. After 24 hours, the dried material is taken out of the oven and cooled to room temperature. Then the materials are kept for 2 hours at 6000 Celsius in a muffle furnace for carbonization process. After 2 hours of carbonaceous processing, the material was extracted, cooled and placed in a magnetic stirrer at 80 degrees Celsius for 30 minutes in a beaker containing 3N HCl, 3N is normality, HCl, followed by repeated distilled water 4 to 5 times or 1 at pH 7 for rinsing. The materials are then placed in the oven for 12 hours under 110 plus or minus 5 degrees Celsius to dry. After 12 hours of drying the oven, the materials are taken out of the oven and used for further study. The cost incurred for procuring, treating and converting it to activated carbon is 265 per kg. That is 265 rupees per kg of activated carbon using areca nut husk. Whereas commercial activated alumina, which is also used to filter water in the urban areas, costs 965 per kg. By using 1 kg of areca nut husk, we are able to treat 250 liters of water without decreasing the efficiency of areca nut husk activated carbon. Thus, we are making it economically viable. So, in normally we use activated alumina, which costs 965 rupees per kg to purify water. But as we are in rural areas and we are trying to make it economically feasible by using areca nut husk as a precursor for activated carbon, we are just spending 265 rupees per kg to convert the uh, areca nut husk to activated carbon. And last is a filtering process. When we're done making the activated carbon, we use the clay pot to filter it. there is a top part of the clay pot, and then there is a bottom part. We fill a cartridge on in the top part. As you can see, this is the cartridge. The top and bottom of the cartridge is filled with sand and activated carbon respectively. Is filled with sand and activated carbon respectively. Like this, here's sand and here's activated carbon. The amount of activated carbon and the sand taken to fill the cartridge is 40 grams and 60 grams respectively, which are filled layer wise. The cartridge is then placed in a hole provided in the lower part of the upper unit of the clay pot. Like this part, we place the cartridge in this part. Water samples are poured into the upper part of the filtration unit. There's the upper part, right? We pour the water from somewhere around here, which then passes through the cartridge, that is sponge, sand, then sponge, and the activated carbon, and it gets filtered through it. The subsequent water which is collected is controlled using a tap. Yeah, use a tap to control the water that is gathered here after filtration. So next we go towards results and discussions. So A, characteristics of prepared activated carbon. The acquired activated carbon put under an SEM, scanning electron microscope. Images clearly show the absorbance, surface texture and porosity with the holes and small openings. These are all facts that we observed. The surface area of activated carbon passing through 75 millimeters and 90 millimeters found to be 183.73 meter square per gram and 169.43 meter square per gram respectively. The moisture content was found to be 5.31 and 7.18 for the activated carbon passing through 75 mm and 90 mm respectively. The ash content was found to be 22.92% and 34.53% for the activated carbon passing through 75 and 90 mm respectively. The low moisture content and ash content indicate that the particle density is relatively small and that biomaterial should be the best raw material to use as adsorbent in the filtration process. So the biomaterial, that is the areca nut husk, is the best raw material to use as an adsorbent in the filtration process rather than alumina. The lower the ash value, the better the activated carbon to use as absorbent. So the ash value is inversely proportional to the to be better activated carbon to use as absorbent. That is, the lower the ash value, the better the activated carbon is to use as an absorbent. So these are the figures and diagrams. This is for the 75 mm passing activated carbon at different magnifications. This is a 75 mm, which is like smaller than this one, and this is a 90 mm pores. Like these are the 75 mm pores, and these are the 90 mm pores, and all these facts are done for both of these pores. And for B, groundwater physiochemical analysis. For collected wait a minute, yeah. For collected groundwater, alkalinity, acidity, and total hardness and chloride parameters are checked after treatment with activated carbon. That is checked after 9 times we repeat this process, they are checked. And average is taken. The hardness of water is found to be 262.3 milligrams per liter before and after treatment. Before and after treatment, it is 245.1 milligram per liter. Alkalinity, these are all facts. These are just facts. That's it. Alkalinity is found to be 219 milligrams per liter before and after treatment. Before and after treatment, it is 145 milligrams per liter. According to Indian Standard Code 10500, is through 2012. The hardness of the water above is desirable limit, and the alkalinity after treatment is at desirable limit. So this Indian Standard Code, this law is about what do I tell you? Yeah, this law is about the contents of the water and how much content of each chemical slash element, chlorides and fluorides content is optimal for domestic use. And this is the graph for parameters before and after the treatment. Before they were before the treatment they were not optimal for domestic use, but after the treatment they are somewhat optimal for domestic use. So the conclusions that we draw after the case study of using areca nut husk as an precursor for activated carbon is the results indicate that areca nut husk can be used efficiently for the preparation of activated carbon. Yeah, we've established that. And the SEM electron microscope images shows that the prepared activated carbon shows high porosity and high pore volume of activated carbon passing through 75 millimeters and 90 millimeters. The moisture and ash content in the activated carbon were found to be low for activated carbon prepared from areca nut husk. That is the low when the ash content and moisture content are low, they are the better activated carbon to use for adsorption. Activated carbon made from areca nut husk is able to remove chloride, alkalinity, and acidity at pH 7 to 8 from the groundwater. The locally developed filter unit is environmentally friendly and cost effective. These are my references for all the things I mentioned. I'll give you a minute. Yep. And thank you. And that was my presentation. And that's it.